Assalamualaikum and very good morning class. In this PowerPoint, we will look at some examples on finding Fourier series equations for some waveforms. Before that, let us recap what we have learned from the past two PowerPoints that I have shared with you. The trigonometric Fourier series of periodic signal, which consists of sines and cosines, is shown in this slide. We also discussed on finding the equations for Fourier series coefficients a0, an, and bn. The integration limit are extend from minus t0 over 2 to t0 over 2. However, these limits can span any convenient interval. We also learned that the Fourier series of an even function is expressed in terms of cosine series. The Fourier series of an odd function is expressed in terms of a sine series. Some examples of Fourier series are discussed in the next few slides. Example 1 shows a square wave signal xt with amplitude of 1 and t equal to pi. In this question, we have to find trigonometric Fourier series of the given periodic square wave signal. To solve this example, let us start with some fundamentals for the signal. Let us find 1 time interval t, 2 fundamental frequency, and 3 identify whether xt is even or odd function. Time interval t equals 2 pi, therefore omega naught equal 2 pi divided by t, which equals 1. Xt is an even function where xt equal x minus t. The signs equal to 0, therefore bn equal to 0. To compute a naught, since this is an even function, we can integrate half and then multiply by 2. Since t equal to 2 pi, t divided by 2 equal pi. A naught equal 2 times 1 over t integral of 0 t over 2 ft dt. And if we proceed with the calculation, the value of a naught equal 1 over 2. For an equal 2 times 1 over t over 2 integral of 0 to t divided by 2 ft cos nt dt. And if we follow the equations, we have an equal 2 over n pi times sine n pi over 2. There are three values for an. When n equal even, an equal to 0. When n equal to 1, 5 and 9, an equal 2 over n pi. And when n equal to 3, 7 and so forth, an equal negative 2n pi. Now let us go to example 2. We have to find the Fourier series for the waveform below. It is still a square wave function, but a little bit shifted to the right. As usual, we start with the basic information of the signal. The analytical question for one period ft for the signal can be divided into two. For time between minus 4 to 0, the amplitude is minus 10. For time between 0 to 4, the amplitude is 10. Since this is a periodic signal, ft equal to ft plus 8. The period t equal to 8 seconds, and the angular frequency for this signal is omega equal 2 pi over 8, which is pi over 4 radian per second. The waveform is an odd function, therefore a naught equal to 0 and an equal to 0. only Bn need to be evaluated, where Bn equal to over t integral 0 t ft sine n omega t dt. Bn equal to, if you put the value outside, we have Bn equal to 1 over 4 integral minus 4 to 0 minus 10 sine n omega t dt plus integral of 0 to 4 10 sine n omega t dt. The integration can be simply evaluated. So Bn equal to 2 times 10 over 4 integral 0 to 4 sine n omega t dt. And finally, we have our Bn equal 20 over n pi 1 minus cos n pi for all values of n. The Fourier series in general form for this signal is ft equal summation of n equal to 1 to infinity 20 over n pi times 1 minus cos n pi times sine n omega t. We can also further expand the values of Fourier series coefficients Bn by evaluating the values of n in the equation of Bn equal 20 over n pi times 1 minus cos n pi for all values of n. Before that, please look at the red box on the top right hand side of the slide for the equation of cos n pi. For n equal to odd, we will have Bn equal 20 over n pi times 1 minus minus 1. So therefore, our Bn equal to 40 over n pi. When n equal to even, our Bn equal 20 over n times pi 1 minus 1, which gives us 0. If we try to find the coefficients Bn up to 7 harmonic, we will get B1 equal to 40 over pi, B3 equal 40 over 3 pi, B5 equal 40 over 5 pi, and B7 equal 40 over 7 pi. Hence, the Fourier series can be expanded as ft equal 40 over pi sine omega t plus 40 over 3 pi sine 3 omega t plus 40 over 5 pi sine 5 omega t plus 40 over 7 pi sine 7 omega t. Or we can summarize as ft equal summation of n equal to odd until infinity 40 over n pi times sine n omega t. Okay, let us continue with example 3. In example 3, we have to find the Fourier series for the waveform the same as in example 2, but this time the x-axis in omega t. As usual, to solve, we start with the basic information about the signal. The analytical equation for one period, ft, equal to minus 10 for omega t between minus pi to 0, and then 10 for omega t between 0 to 2 pi. It is a periodic function with equation ft equal to ft plus 2 pi. Therefore, the period is 2 pi and the angular frequency is equal to y radian per second. Next, we know that the waveform is an odd function. So, a not equal to 0 and an equal to 0. Only bn need to be evaluated. And the equation for Bn in this case is 1 over pi integral minus pi to pi ft sine n omega t dt. Bn equal to 1 over n, everything in bracket, integral of minus pi to 0 minus 10 sine n omega t dt plus integral from 0 to pi 10 sine n omega t dt. The integration can be simply evaluated. So therefore we have Bn 2 times 10 over pi integral 0 to pi sine n omega t dt, and then equal 20 over pi times minus cos n omega t over n for 0 to pi, and finally we have Bn equal 20 over pi times minus cos n pi over n plus cos n 0 over n. And since cos 0 equal to 1, we have Bn equal 20 over n times pi times 1 minus cos n pi for all values of n. Therefore, our Fourier series in general form, ft equals summation of n to infinity, n equal to 1 to infinity, 20 over n pi times 1 minus cos n pi sine n omega t. Just like previous examples, we expand the Fourier series Bn, and then referring to equation for cos n pi, it will be minus 1 for n equal to 135 and odd numbers, cos n pi equal to 1 for even numbers. So therefore, in this Fourier series coefficient for Bn, Bn will be 40 over n pi for n equal to odd numbers, and Bn will be equal to 0 for n even numbers. The coefficients are proven 0 for even harmonics, and the waveform has half wave symmetry. Solving the coefficients up to fifth harmonic, we can determine the B1, B3, and B5, just like in the previous examples. Therefore, our Fourier series will be ft equal 40 over pi sine omega t plus 40 over 3 pi sine 3 omega t plus 40 over 5 pi sine 5 omega t. We can also simplify the equation. Ft equal summation of n equal to odd to infinity 40 over n pi times sine n omega t. The final example for this PowerPoint will be until example 4, and example 4 is based on example 1 revisited. The question is to find Fourier series for the waveform below, and we already did the fundamentals of the signals, where the analytical equation Vt equal to 10 for t minus 1 to 1, and Vt equal to 0 for t minus 1 to 3. And our periodic function equation Vt equal to Vt plus 4. The general form for even function with average value is Vt equal to a naught plus summation of n equal to 1 to infinity a n cos n omega t. Okay, we recap. The angular frequency for this example is pi over 2, and the average value a naught equal to 5. And we determine the cosine Fourier coefficients an, and in this case we have an equal 2 over t integral of Vt cos n omega t dt, and finally we have an equal to 5 times sine n omega t n omega for integral of -1 to 1, and what we finally got is an equal to 10 n pi times 2 sine n pi over 2. This is based on our trigonometric identity equation as shown in the red box. To expand the Fourier series, we have an equal to 0 for n, 2, 4, 6, and so forth. An equal to 20 over n pi for n equal 1, 5, 9, and so forth. An equal minus 20 over n pi for n equal to 3, 7, 11, and so forth. This is based on the sine trigonometric identity. Since we have sine n pi over 2, when we substitute n, 2, 4, and 6, we have 0. And for sine n pi over 2 equal to minus 1 for n equal 1, 5, 9, and so forth. And sine n pi over 2 will be negative 1 for n equal to 3, 7, 11, and so forth. Hence, the Fourier series can be expanded as ft equal 5 plus 20 over pi cos. So that's all for this PowerPoint. In our next PowerPoint, I will show you more examples on Fourier series for different types of waveform. Thank you.